real gases. We've been talking about ideal gases, and that's great, but there are real gases. So an ideal gas has no attractions between gas particles and a negligible particle volume. Turns out real gases act a lot like ideal gases at STP, but if we get to high pressure or low temperature, they do not behave like ideal gases. We can kind of get an idea for how ideal a gas is by looking at its molar volume. If you look at the actual molar volumes for these different gases at STP, they are very close to 22.4. In fact, helium hits it right on the nose. This is 22.41, and this one's 22.41. See that chlorine is a little off the mark, but these guys are pretty close. What happens at low pressures? At low pressures, the molar volume is nearly identical to that of an ideal gas. But as the pressure increases, if we look here at argon, as we squeeze them together, the molar volume of argon becomes greater than that of an ideal gas. And that's because as things get more and more crowded, the argon atoms themselves are going to occupy a more and more significant portion of the gas volume. They're not actually negligibly small anymore. Their size becomes significant. And so that causes the actual volume to be greater than that predicted by the ideal gas law. So real molecules take up space. So as we go to higher pressures, we see that the volume of the argon is above what's predicted because of the actual space that the argon molecules themselves take up. They're not molecules, they're atoms. Johannes van der Waals modified the ideal gas equation to compensate for this effect. So here's the ideal gas law, and he added a factor in here. You could think of it as a fudge factor to correct the volume. There are certain instances where you need to know what is the volume. So B is called the van der Waals constant. It's different for every gas because their molecules are different sizes. Each gas is going to have a slightly different variation from the others. So we know that that exists. High pressure causes the volume to be higher because the gas particles are getting close together and now their volumes are becoming significant. At high temperature, the pressure of the gases is also nearly identical to that of an ideal gas. But when you get to low temperatures, the pressure of gases is less than what you expect. This is because at lower temperatures, the gas particles are moving more slowly. And so they're going to spend more time interacting with each other and less time colliding with the walls, causing the actual pressure to be less than that predicted by the ideal gas law. So van der Waals also made a modification to account for this. A is another van der Waals constant, again different for every gas. In this graph we see pressure as a function of temperature, and we see that xenon has a lower pressure than predicted by an ideal gas when we get down here. Up here they're essentially the same thing. Yeah, I thought that was awesome too. And so here they're subtracting a term from the ideal gas law. You can combine these all together and we get the van der Waals equation, and this will account for the behavior of real gases. Doesn't that look like a lovely mess? And here's a table of all the constants, and that's just fabulous. If we plot PV over RT, what does PV over RT equal? Well, yeah, but the number of moles, right? So PV over RT versus pressure for 1 mole of a gas. For an ideal gas, we would expect that N from the ideal gas constant, ideal gas law, would be the same. It'd be 1 all the way across. So this tells us what an ideal gas would look like in this graph. And what we find is that some of the gases are above the line and some of the gases are below the line. A curve below the line means that the important factor in its difference is intermolecular attractions. water has significant intermolecular attractions. As you cool a gas down, and it has more time to interact, those intermolecular attractions become more significant. Curves that are higher mean that the most important factor is molecular volume. So for xenon, up here, the most important factor is molecular volume. Helium doesn't really do much of the intermolecular attraction stuff, and so its whole deal is the molecular volume. See, now we should have the cheering. Where's the cheering now? Yay! Thank you.